Alright, so in this lecture we will be talking about relative address. Now, at this point we know about the branches, right? We looked at flags, and using the flags we know how to determine whether the branch will occur. Now, if you have noticed something, let's say for an example, if you look at these lines, we have 5 lines here, right? Now remember, every line has an addressing mode, right? We know that some of the lines has immediate mode, or extended, direct, or inherent, right? Now if you look at these lines, you can see that the first 2 lines are immediate, right? This number line 4 is also immediate. This is a label here. But if you notice, can we tell what is the addressing mode of line number 3 here? We actually cannot, because this is actually none of it. I'm saying this is not immediate, this is not direct, extended, or inherent. So all the instruction that starts with a branch, like this one, that has a new addressing mode that we have never used before. That is called relative addressing mode. Okay. Now, all the instructions where you have a branch or jump, okay, I think we now have a list of branch instructions, right? So all the instructions those are branch, that is actually the relative addressing. So in this lecture we'll be actually extensively talking about the relative addressing and how we actually find the object code of those, because remember, we can actually write one object code for every line, right? And the object code we write based on the opcode given in the set of instruction, right? We can also write the operand from the instruction. But surprisingly, if you look at this line, if you go to your set of instruction, you can always find the opcode for BMI, because all the branches we have the opcodes, right? We are given the opcode, but you don't know actually what will be the opcode for the labels, because the label is a name that is actually given by us, right? So for an example, if you go to your set of instruction and if you look at the column 5, you can find the opcode of every instruction, right? But you don't know how to write the operand for this line, because this is a label, and the label is something like a name, right? And that is given by us, so we can give whatever the name we want, but we don't have any idea how to get the operand for this line. Because for an example, if you look at the other lines, let's say the line 1, the operand is 20, right? Line 2, you see the operand which is 34, right? In the line 4, you can see the operand which is 48, right? Now, how do I actually write the object code for the relative addressing? Again, as you have remember, I think we did it in the quiz 2, that was at the very beginning. We tried to write the object code for the couple of addressing mode instructions. So we have seen that the object code can be only 1 byte. For an example, in case of inherent, that was only 1 byte, right? Some of the object codes are 2 byte, especially the ones like direct, right? And some of the object code like extended are 3 bytes, and the immediate is sometimes 2 bytes and sometimes 3 bytes. But we never have seen, again, as I said before, that we have never seen the relative addressing. In case of the relative addressing, every object code must be 2 byte. Okay? So as usual, you can guess the first byte is actually the opcode, which we actually get from the column 5. If you have your set of instruction, you can check that in the column 5 you are given all the object codes, I'm saying all the opcode for every instruction. Okay? So we can easily get the opcode from there, whatever the branch instruction we use. But the problem is with the relative address, because the second byte, which is actually the operand, is called the relative address. Okay? So again, as I said, as I'm claiming that we'll be writing 2 different bytes, right? The first byte is your opcode, which is given in the column 5. Second byte is an address that is called relative address. Okay? And interestingly, we actually have to calculate it. Okay? We can find it just using a calculation. How can I do it? Let's look at an example. Again, I repeated the previous example here. Okay? But this time, with each lines, I also have written the addresses of the line. Now, again, when you go to the lab, you do the labs. Remember, we actually start the program from some address, right? Most of the time, we start the program from an address, address called D000, right? That is where actually your program is located, meaning that is actually the first byte where the program is being loaded. So after D000, you have consecutive bytes. You have all the address, all the program, meaning all the instructions. The object code of the instructions are stored. Now, for an example, for this program here, we have 5 lines. It's not a program; it's let's say a segment of the program. We have 5 lines. Now, D010 is actually the address of the first line. And remember, as I said, every line has, based on the object code, it might be 1 byte, it might be 2 byte, it might be 3 byte, right? If you look at the first line, it's actually immediate and it's actually 2 byte, right? And that's how it will take what? D010 and D011, 2 byte, right? And automatically the next line will be starting from D012. And that will be taking 2 more bytes, which will be D012 and D013. Automatically the next line will be D014, right? You see what I'm saying? And that's how I actually listed some addresses here. I'm saying the addresses of the lines. Now, again, if somebody tells me, I know that the object code of the line 3, which is the branch instruction, will be 2 byte, right? But I don't know what the bytes will be. I just know, okay, I know the first byte will be opcode, which I can get from the column 5 for BMI, right? Or for any branch instructions, I know that. But I don't know exactly how I get the relative address at this point, right? Which is actually I'll be writing for the labels. Now, for an example, in this specific, line, the label is save, right? But if you look at the save, that is just a name given by us. I can give any name, whatever I want, right? It's just a label. But how do I calculate it? So I just highlighted the relative address will be calculated just for the word save, just for the label save in this case. Okay. Now, how can I really calculate it? Now, to calculate this, I need 2 specific things. Number 1, I need the address of the line where where the branch instruction is located. Right? I need 2 different things. I need the address of the line where the branch instruction is located. Look at this, I marked it, okay? Now, this is actually the line where the branch instruction is located, right? BMI, right? Now, so this is called, for an example, source line, but because this is the line where your branch instruction is located, okay? And as you can see from here, there is a label here, right? That label is also repeated in somewhere else, right? Because since you are saying, okay, branch to that label, in your program, that label should be in a different line for sure, right? Because that's how your program actually will branch to that line if it actually make the branch, right? So, as you can see, the label is again here, right? Save. That means this is actually your destination line. That means this is the line where your program will jump if the branch actually makes, based on the flags or whatever the condition we have, right? You see what I'm saying? So I need to know 2 different address of the lines. One is the source line where the branch is located. One is the destination line where the branch will actually jump if the branch occurs, right? Now, from those 2, I actually wrote down, look at this, at the bottom I wrote down the source address, which is D014, I got it from the code, right? And the destination address, D018. Okay? So I just got those from this, the block of code I'm given. Now, once I know the source and destination, what I need to do is I just have to plug this into a very simple formula. Now, here I wrote the formula for you to calculate the relative address. Now to calculate the relative address, the formula is very simple. The formula is actually RA equals to DA minus PC. Now what are these RA, DA and PC? I wrote it down again. RA is your relative address you are looking for. Okay. DA is the destination address. Remember, we just got the destination address, right? The line where your branch is jumping. And PC means program counter contents. I actually don't know how I get this PC yet, right? But just before I start, the further showing how I get these, just 3 things to remember. In general, all the addresses that we have, anytime we talk about address, in general, all the addresses are 2 byte, right? Remember, all the addresses are 16-bit, right? 2 byte. But the relative address is always 1 byte. See, I marked it. Relative address is always 1 byte. Now, how it is possible that all the addresses are 2 byte, but the relative address is 1 byte? Is what is the reason behind? The reason behind is the relative address is not actual address. It's not a real address. Is an address actually calculated artificially? That's why it's actually 1 byte. It doesn't have to be 2 byte because it does not. It's not like the real address we have in memory locations. Okay. Now let's look at how I actually plug the whatever I got from the remember I got the destination address, I got the source address, and how I plug it there. Now this is how I actually do. Remember I got that 2 blue things, right? This is your source address, right? D014, right? And the destination address is D018. I just got from the question because these are the 2 different things I need to know to calculate the relative address. So what I did is I first listed the ones that I'm given. I'm given the destination address, which is D018. I'm also given the source address, in short SA, which is given D014. And then I calculated the PC. Now this is the formula to calculate the PC. This is a very simple formula. All you have to do is PC equals to source address plus 0002. It will be always like that. It's just a formula. Okay? That's PC means again what? The program counter. Remember, it's actually the content of the program counter register. Remember there was a register called program counter. So PC equals to source address plus 0002. So I just plug the source address because I know the source address from is given, right? Which is look at this, is given D014, right? Source address. So I just plug the source address here and added D0002 because that's the formula, and then I got the PC, which is D016. Now once I know that this PC, all I have to do is just plug it to the original formula to calculate the relative address which was given in the previous slide, right? The relative address is nothing but destination address minus PC. So I know the destination address. Look at this. I know the destination address, right, which was given in the question, D018, right? So I plugged D018 and I subtracted PC that I just got in the previous line, right? I just got the PC in the previous line. Oh, that belongs to the formula. That's part of the formula. So you don't have to. Yeah. It's the formula for the PC. The 0002. That's the formula for the PC. Okay. That will be always the formula for the PC. So once you do the subtraction, you got it's just a hexadecimal subtraction. Once you do the subtraction, you got here 0002. But remember, we were calculating the relative address, right? As I said in the last slide, the relative address is always 1 byte, right? Remember? But this is like 2 byte here, right? So how do I actually get the 1 byte from here? So interesting thing is, whatever you get from the calculation, it will be always 2 byte, but you will be always dropping the higher byte. Okay? Higher byte of the difference is dropped always, leaving the low byte as the relative address. That means I'll be actually dropping the higher byte. Do you see I dropped the higher byte, which is 00, I dropped it, and at the end, the relative address will be actually 02. That's it. That's what I was looking for. Okay. So the relative address is just 02 for this problem, for this case. Okay. That's our relative address. Now, one more thing that we must need to know. So I actually, this is a reminder, okay? Remember, I know that we have to drop the higher byte, right, of the difference to get the relative address. But that high byte, what I'm going to drop must be 0, 0 for positive branches and FF for the negative branches. Now, what is the positive branch? Remember in the last lecture, we are talking about the branches, right? Whenever you actually branch forward, meaning your label is actually downward, that is actually the positive branch. When your label is backward, because your program is actually branching back, that is actually the negative branch. But don't worry about the positive and negative branch too much here. All you need to see is whenever you are dropping the higher byte, you're dropping your higher byte must be 0, 0 or FF. Now what happens if they are not 0, 0 and FF? Because in this case it was 0, 0, I dropped it, right? In some other cases it might be FF and I'll be dropping it for sure. But what happens if it is not 0, 0 and FF? If it is not 0, 0 and not FF, your calculated relative address is actually illegal. So that means whatever the relative address you got, that is not right. And interestingly, there is no way you can get the relative address in those cases. Okay? So now I have everything written formally in one or two slides how we actually solve the problem. But actually, this is actually the repetition of whatever we did so far. So this is our formula to calculate the relative address. So we know that relative address means from the formula is destination minus PC. So as you can see, we actually have three variables, right? Destination address, PC, and relative address. So to get any out of these three, you actually need to know the other two, right? That's always we have to, right? Whatever you are calculating from here. So if you are calculating the relative address, you actually need to know the other two, meaning the destination address and PC. Or if you have to calculate the destination address, you will actually have to know the relative address and PC, right? So you actually have to know any two out of these three to calculate the last one. Now, let's say if I calculate, if I try to find the relative address, how do I get it? I first actually look at my problem and see and find out what two variables are given, meaning which two variables are given. It might be any two out of three, right? And then, based on that, if I'm given the branch instruction, meaning the source address, the line where the branch is located, I'm given that. If I'm given that, I can always calculate the PC, right? Because the formula of the PC is based on the SA, right? Which is actually SA plus 0002. So if the relative address is given, but if the relative address is given in the question, okay, remember the relative address will be always given as 1 byte, right? It will be given as 1 byte. But when you plug it into the formula, if you have to, you will be always plugging it as 2 byte, right? How do I make 1 byte to 2 byte? Because so what I can do is I look at the relative address, okay? It's just a 1 byte address, right? If the relative address is positive, it may be positive and or negative, right? If the relative address is positive, I actually plug 00 as the higher byte. You know that, right? We actually have to make it 2 byte when I plug it into the formula. So if it is a positive number, I plug 00 for the higher byte. If it is a negative number, I plug FF as the higher byte. Okay? And then, as I said, out of the three, I now know 2, right? Whatever the 2, it might be I know, let's say, the relative address or PC, I'm looking for the destination address, or I might be knowing the destination address and PC looking for the relative address, right? So I plug 2 and then I find the third one. Because all you have is 3 variables and you just need to know 2 out of 3 to find the third one. Okay. Now let's look at some problem here. Okay. Again, from the problem, I have to actually find out what is given, right? What are given, right? As I said, I'll be given 2 out of 3. Now let's see what 2 I know. Now assume that the opcode of a branch instruction is located at the address 0051. Now what is this address? What is this? Is this the branch location, right? Because this is the line where the branch instruction is located. So that is actually your source address. Now the destination of the branch is 0063. The destination of the address is 0063. That means this is your destination address, right? So you have to compute the relative address. You have to actually calculate the relative address that will cause a branch from there to there. Okay, now we know the formula here. Okay, now let's write down what is given, right? We know that the source address is given, which is actually the branch location, which is 0051, right? Is given in the question, right? We are also given the destination address, right, which is 0063, is given in the question. Now I can calculate the PC, which is coming from the formula, right? We know the formula for the PC, and formula for the PC is very simple. We just have to add 2 with the source address. Source address plus 0002, right? That's a formula. So I just plug the source address here to calculate the PC, and I got the PC, right? Which is 0053. Which is 0053. Once I did it, I know how to calculate the relative address, right? So I just plug the DA destination address and program counter, right? I do a subtraction here, right? Based on the formula. Once I do the subtraction, I got the relative address. But remember, I will be always getting the relative address as 2 byte. But relative address is actually 1 byte. How do I get the 1 byte? I have to drop the higher byte, right? I have to drop the high byte. So what is the high byte here? So notice the higher byte is dropped, okay? But be careful. Whenever you drop the higher byte, it must be 00 or FF. If it is not 00, not FF, your relative address is not, you cannot calculate the relative address. The relative address will be illegal, right? Let's look at another example. So in this question, I'm given what? Let's look at the question. A branch instruction is located at the address 0135. That means your source address is given, right? And the relative address of the object code is D2. That means the relative address is given as well. Now what I'm looking for is actually the destination address. That means DA. Do you see the difference in the question? The last one we were looking for the relative address, but now I'm looking for the destination address, right? So I'm given so what I'm given, I'm writing here at the beginning. I'm given the branch location, which is already given in the question, which is 0135, and from the branch instruction I can always calculate the PC, right? Using the formula, which is just adding 2 with the source address. I added 2, I got the PC, right? And I'm given the relative address. But remember, the relative address is always given in the question as 1 byte, but when I plug it into the formula, I have to always plug it as 2 byte. How do I make it 2 byte? I just look at the relative address. D2, right? D2 is positive or negative? D2 is a negative number. Now, as if it is a negative number, the high byte will be FF, right? We know this, right? I just, remember in the other slide I was talking about this. If the relative address is positive, the high byte will be 00. Since the relative address is negative here, which is D2, so the high byte will be FF. So I actually plugged FF because I know that the relative address is negative, right? And then I actually have to find the destination address. So I just first wrote the formula I know, right? And from the formula, I just added the PC to both sides to isolate the destination address. So this is actually the formula for the, I just tweaked and twisted the formula, right? Because I just added the PC to both sides and I got the destination address formula. Now the formula for the destination address is relative address plus PC. So I now know the relative address. I also know the PC. I added and I got the destination address, which is 0109. But be careful, don't drop the higher byte here because this is a real address, right? This is a real address. You always drop the higher byte only in case of relative address calculation. So you are not calculating the relative address here because you already know the relative address. You extended the relative address to the 2 byte and you plugged it into the formula. So you are actually looking for the destination address, so which is actually a 2 byte address, and this is your answer, 0109. Any question here? Let's look at another example here. Okay, let's say in this question I'm given the branch instruction is located at 0300. Now what is this? That means your source address is given, right? You are also given the destination address in the next line. The destination address is 0010, and you actually have to calculate the relative address using the formula, right? It should be very easy, right? So I just know I can calculate always the relative address. I'm saying the PC from the source address, right? Which is actually just adding a 2, which makes it 0302. And then I also know the destination address from the question, and I'm looking for the relative address. I know the formula. I plugged it into the formula, and I did the subtraction based on the formula, and I got an answer which is FD0E. Now, what is the problem here? To get the relative address, I always drop the higher byte, right? But notice the higher byte. What is the higher byte here? FD, right? Remember, as I said, higher byte must have to be 00 or FF. Now in this case, higher byte is neither 00 nor FF, right? That means what? Whatever you calculated as the relative address, which is actually 0E, is actually illegal. It's not right. And there is no way you can make it right. So how do you answer this question? All you have to do is, if you go to the quiz section, you will see that if your relative address is illegal, then you actually have to type ILL. So you will be, look at this, I wrote it in each question. This is how you'll see the question. This is a sample question. So if the branch is not legal, type ILL. So in this case, you will be actually entering ILL because whatever you got from the question, which is 0E, is not legal. So you have to identify it, okay? So this is an illegal address, so you just write ILL, okay? Now let's look at another example, but in this example you see the question looks a little bit different because instead of just telling the addresses in the question, we actually gave you the code. This is actually the same thing, but you have to find those addresses from the code. Look at the question here. You have to calculate the relative address for the branch instruction above. Now, how many branch instructions you have? You actually have just one branch instruction here, which is in line 4, right? That's the only one you got, and the line 4, which is BRA. Do you see it? And if you look at the left side, what you are given is actually similar to how you see the list of lines with the codes in the list file. Remember, in the list file, in the left side, you have all the addresses and the object codes. So these are actually the addresses in the first columns of the lines, okay? And the next bytes here, for an example here, 96A3 is actually the object code of the second line, and 9B57 is object code of the third line, right? And 20, I don't know what it is we have here because this is the question mark where I actually have to find the relative address for this place, right? So that's why I put a question mark here. So I'll be looking for this question mark byte, which is actually the relative address for the label skip. Do you see the label here, which is skip? And for that label, I have to calculate the relative address, and that relative address will actually fill this byte in the object code. But how do I get this 20? I got this 20 from the column 5 of the set of instruction for BRA. So it's easy because I just looked at the column 5 for BRA, which is given in the set of instruction, which is 20. So I know it from there. But what I don't know is the relative address, the question mark byte, which is actually for this skip. And I'll be looking for that one. Now again, to answer this question, I first have to find out what I know. Remember what I need to know. I need to know the source address, right? I also need to know the destination address. Now what is source and destination here? Just from the code, how can I locate it? Look at this. This is actually my source address because this is the line where the branch is located, right? So the source address is actually 0040. Now where is the destination? If you look at the branch instruction, this is your branch, right? Skip. I'm saying this is the label for the branch, right? Now if you go here, this is the line where you have the label, right? Skip. So this is actually your destination line, and this is your destination address, which is 004B. Now you're done, right? You pretty much know what you need to know, right? So all you have to do is simple calculation, because you just have to find the PC based on the source address. You know the source address, which is 0040. You add 2 based on the formula you know for the PC. Once you know the because I know the destination, right, which is skip. That's the label, right? Yeah, whenever you see the label, that you will be looking at the very leftmost address, yeah, because that's your destination line. Yeah, wherever you see that label in the left side, that is your destination line. Okay. Now, once you know the PC, you calculate the. Once you know the source address, you can calculate the PC. You know the destination address from the code, right? Now all you have to do is just plug it into the formula for the relative address. You calculate the formula and drop the higher byte. Don't forget to drop the higher byte, right? And when you drop the higher byte, be careful, it must be 00 or FF. So since this is 00, it's safe to drop. I dropped it, and I got the relative address, which is actually the answer to this question, which is 09, right? And that's all about it, okay? So now we actually know one more addressing. Again, remember at the very first time when we were talking about the addressing mode, I said we actually have 6 addressing modes. But we only explored 4 out of 6. We just talked about the immediate, direct, extended, and inherent. Now this is the 5th one, which is the relative addressing. Okay? Now if you look at all these lines, you can actually tell what are the addressing mode, right? First line, the addressing mode is direct. Second line, the addressing mode is direct. But the third line, not the third line, it's actually the 4th line. 4th line, the addressing mode is relative. And this is how you actually calculate the object code for the relative addressing. Okay? And see, we waited so long to understand it because we actually have to understand all the way up to branches to actually calculate the relative address. And that was the reason why we did not explore the relative address at the beginning. But we still have one more relative address left, okay? Because we are not done yet, because we just, explored 5 out of 6, okay? And you will see it soon, okay? I know that some of you probably cannot wait, but we'll see it very soon. Okay, now we have 2 quizzes for this part. Again, you will see pretty similar questions that you have seen in the examples, right? In the first quiz, you'll be given, in the question you'll be told what is the destination address, what is the source address, or what is the relative address. You have to find the third one. In the second part of the quiz, instead of telling those addresses, you'll be actually given the code. And you have to find the addresses from the code and plug it into the formula. You are done. Okay? Let's go to the quiz section and jump onto these and then finish these ones so that we can understand the lab 3. I'll probably also talk about the lab 3 today so that we can start the pre-labs before we go to the lab next class. Okay?